Okay, so issue 6549 is something that's been requested a couple of different times in various places. So I recorded this issue for it. What you can do at the minute with local arrays in CUDA, which is an array that's private to the current thread, is you can allocate them with a size that is static. So I could say nx, I can't actually say nx and ny here, but I could say some actual integers like 2 and 3 or whatever. This will fail to compile at the minute because it doesn't allow you to dynamically size the local arrays. Dynamic allocation is supported on any device that anyone is using now. So it'd be good to be able to try to support this. So I've got an example of code. This is a kernel that does something with a local array. So we create a local array. At the minute, I've got it statically sized, so 2 by 4. And then it loads some data into the local array, does some computation on it there, and then writes it back to global memory. The idea of doing this is so that we can have this kernel compile and not just have the local array declaration optimized away. So hopefully I'm actually testing everything sort of end to end. And if I try to run that now, was this 6549? And that, oh, try to run that now. If I fix that and try to run that now, then it compiles without an issue. If I try to make the array dynamically sized, by the way, everyone who's on the call, feel free to jump in with questions at any time. If you have a question. So let's get rid of this static sizing. We'll make it so that we're passing in the size of the array instead. Oops. I think if we fail this now, sorry, run this now, we should get a typing error. And the typing error is telling us that we don't have an implementation of the local or CUDA.local.array function when the argument is a tuple of 2 int 32s. Before it was a tuple of actual integers, so that wasn't a problem. So the first thing we'll need to do to get around this error is to add an implementation of the typing for this for when we're passing variable integers to CUDA.local.array. I'm going to head over to the Numba source tree and have a look at that. Oops. So the typing for most things in CUDA is in the CUDA/CUDA-DACL module. And I should add also, I'm coming to this a little bit cold. I haven't really prepared for this. The idea being that I should be able to show you exactly my thought process when I'm working through these things, but it might also mean that I wander around a bit lost for a little bit. So I'm just going to search this file for local array and see if I can turn up what the where the typing implementation is. So I guess I found it here. The typing key is CUDA.local.array. So this class should type for CUDA.local.array. It's a subclass of CUDA-array-decl. So I want to be looking at the generic method of CUDA-array-decl just here. And what it will do when it's typing is it will follow through this logic. If we've got an integer, it's okay. Or if it's a tuple of integers, then it's okay. What I'll do is relax this check so that what I think I want to do probably is just get rid of it. If let's just pass that check for now. So if it's an integer, then we'll go into this branch, and then eventually we should fall through into the rest of the logic for the function. And then in the case where it's a tuple, we'll change this checked. Instead of checking for integer literals, we'll just ensure that they're integers. So I think, well, this is my first attempt, and that might get us through the typing. So if that's been successful, then we should get a lowering error at this point. No, because oh yes, sorry, we've got a lowering error. So we got through the typing there. So next, the thing that we need to address is the implementation of the lowering. So the lowering, in fact, before I go on, are there any questions about the changes that I've made or the typing implementation there? Okay, I'll have a look. The lowering is mostly in Numba CUDA import. So I'm going to be looking for a lowering for local.array. So I'm just going to search this file for local again. And the lower decorator is adding this function, CUDA local array integer, to the lowering registry for CUDA. So what it's telling Numba is you can use this function to lower CUDA.local.array when the arguments are an integer and then any other type. So at the minute, we won't be finding that. At the minute, that'll only match for integer literal. So let's loosen it up to an integer. I think what we'll probably do is then check if the argument is an integer literal, so that this literal value check, literal value usage will still work. So if it's an integer literal, we'll follow the old path and use the literal value. If not, for now, I'll just pass over that and leave a note that we need to fill in the implementation there that's going to figure out what the length should be when it's not a literal value. Now, because my example is using a unituple, I'm also going to need to edit this implementation. So that lowering is going to lower only for when you've got an integer as the shape, but we've got a tuple as a shape, so we want to use or modify this ptx alloc array function as well. So there's no check for integer literals here because the typing's already checked whether it's a tuple of integer literals or not, so we don't need to modify the signature. But I will need to make a similar modification for the computation of the shape. So I think what I might do is start off with a shape, an empty shape array, and then what we might have is where the signature's got some arguments that are literals and some arguments that are not literals. So we should iterate over each of them and handle them individually, depending on whether they're literal or not, and then add them to our array of shape. We'll check if our current value is a literal again. Think of a variable name. Call it sh for now and think of a better name in a minute. So that's just pretty much then the other case that we now need to handle is where it's not an integer literal, then we need some other implementation. We'll implement in a minute. I think what we've just done so far with that loop is basically implemented this list comprehension for the shape, but added in our check for integers. What shall I do now? What I'll do is I'll just put a breakpoint in. Excuse me, put a breakpoint in there. Then hopefully when I run the example again, we should end up just here. So make sure that at least my logic is okay so far. Yes, we are. So we just hit this breakpoint. Ideally, we would figure out what the shape is, what this shape value should be. I think at the minute the argument s is our argument s. Yeah, it's an int 32, so we wouldn't get the literal value, but we do. So what we've got here is the type of the argument, but what we're actually going to need is the actual argument itself. So we should probably, in this case, zip the arguments together. So s, well, type would be a better name. Args. I'm just going to quit this now and then run that again. Hopefully we can, oops. Okay, why has that gone wrong? I don't know exactly, but I'll put my breakpoint just here instead and see. I think the problem was with iterating over arg0, and it probably wasn't something that wasn't what I expected it to be. So args is 0 is what is it? Why have we got that? I think the signatures arguments were so if I've got some tuple arguments, what do I do to iterate over their actual values? If you know the answer, then do jump in and tell me. Into IPython. So
you need the tuple unpack.
Right, okay. Is that CG utils?
Look it up.
All right, so if we do something like CG utils that unpack tuple builder, arg0 guess count equals 2. There we are. So I should probably do that, right? CG utils that unpack tuple, and then my count should be equal to the length of
according to the type.
Yeah. So oh, wait a minute. The type is going to be what have I got the type in? It's sig.args0, isn't it? Is it count? All right, okay. It's looking increasingly messy, but hopefully that will get us to where we want to be. So I'm going to quit that and then restart in the debugger. Oh, so just to recap, if we're doing a local array allocation where the argument is a tuple or unituple, then we unpack that tuple to get each of the values. Then we iterate over the types of those tuple values and their actual values. If the type is an integer, then we use it, integer literal, we use its literal value. If not, we'll fall into this other branch that we yet to implement. So I'm just going to step through this line by line and see if it blows up before I get to the else branch. That's looking more promising. Okay, so we've ended up in that branch. Now, the question would be, what do we do in this branch when the value is not not constant? I think let's have a look what val is. I would guess that we probably just want to make the type shape should just literally be what the value is. Because then there's this generic array allocation function, which is a bit further down this file, where we're going to pass this shape into. And I think that it's there that we're going to need to make a modification to make the allocation a bit more dynamically. So let's jump over to where that function is now. And oh no, I said that in a minute. So this generic array function appears to be aimed at generally allocating an array of a static size, although we have got this canned in sized argument. So this canned in sized argument is normally used for dynamic shared memory where you're passing a shape of 0. So I think I might just pop back to the call and in fact let's assume at the start of this loop that we're not going to have any dynamic allocation. And then if we fall into this branch where we're using a value and not a literal, then probably need to set it so that we do think we're going to be dynamically sizing our array. So so now, at least in generic array, we should know at this point whether we're going to be dynamically allocating a local array or statically allocating one. We'll also be able to tell whether it's a local array or not from the address space argument. So I've put the breakpoint just as we enter this function, and I'm going to quit here and restart the program just so we can start stepping to where we were. Any questions at the moment just before I start doing that? Can everyone hear me? I was speaking to myself.
Yes, I can hear you.
Okay, great. Okay. Where are we? Oops, I've left a breakpoint in the wrong place. Sorry. Let's get rid of that one and start again. Okay, so now we're inside generic array. And I think we're going to fall over straight away because this reduce operator is not going to like reducing something that's, not going to like reducing that. So we need to change this because it's assuming that we've got a shape that's just a bunch of integers. So I suspect that if we just avoid doing that when we are having a dynamically sized array, this might break something for shared memory allocation because this generic array function is used for that, but it will get us over the hump for now. And then we can go back up and fix this logic later if it does break some of the shared memory tests. The next check is to see whether it's allocating dynamics shared memory. And that is going to be true. Now we're going to end up. Are we going to end up? What we might want to avoid doing is ending up with dynamic SMEM being true when we're actually allocating dynamic local memory. Where does what happens to LM count inside this function? Gets used for creating a type. Anything else? No, that's it. So what I'm tempted to do is maybe just move the rest of this. Check. No, it's definitely going to break things. Finding it a little bit hard to explain my thinking here at the minute because I don't quite know what I'm thinking. Where does dynamic SMEM get used? Oops. Just there, so it sets the linkage of that memory, and it also does that. So maybe I'll guard this with a check where what I'm thinking here is if maybe I've got that condition wrong. What I want to avoid is this check. I want this check to not run if we are if we do have a dynamically sized array in the local address space. I think now I've made those 2 changes. I think I'll just restart the debugger and start stepping through to see what we end up with. So hopefully this first check is going to get skipped over in this case. Yep. And is the second check going to get skipped over? Yes. Okay. So I've just realized that now means that dynamic SBIM is going to be undefined. So let's just make sure that we don't accidentally leave that on set. Definitely not dynamic shared memory if the address space is local. So starting the debugger again, skip over the first check. This time we should be saying that it's not dynamic shared memory. What's this next line? I think this check over these 3 lines is fine because it's something to do with checking the D type, nothing to do with the shape. So we can go through that. The next place we're going to run into a problem is just here where we're going to use lmcount to determine what the type of what the array type is. So I think I'll probably just get an exception here because I haven't set lmcount. Yeah, okay. So maybe let's change this condition. So if we haven't got a dynamically sized array, what do we want to do with the element count for the type? It's not going to be it's not going to be constant. I wonder if that should be 0 if we don't know what the element count is. So ir.array type, I believe, is a type from LLVM Lite. So let's just go and have a look at the LLVM Lite docs. Okay. Element is a type of every element. Okay. I think that probably the assumption here will be any further details. I should refer to the LLVM documentation. So I'm looking for 7.0.1 language reference manual because NVVM is based on LLVM 7. Let's have a look at the array type there. Single dimension variable size array addressing can be implemented with a 0 length array type. Okay, so our local dynamic arrays are actually going to have more than a single dimension. But I think what we'll do is pretend for LLVM's purposes that this is a single dimension with enough elements for all the dimensions, and then we'll be doing the index computations ourselves to access elements in a more multi-dimensional fashion. So let's go back here, and if it is a dynamically sized local array, then we'll just say lmcount equals 0. So let's go with that. I'm going to start the debugger again, start stepping through, make sure that everything behaves. So element count is 0. It's not dynamic shared memory. That's the checks for the type. Should be able to create our LLVM array type safely. We do. Now we're in this branch just here, which says if we're in the local address space, do this. I think let's just have a little look further down what happens after that. Actually, let's not. Let's just think about what's happening inside this case. So allocate once is going to allocate a fixed size local array. So I think what we need to do here is add another condition, which checks to see if we're dynamically sizing the array. If we're not, then we can use the same code that we had there already. So that's the logic that we need. What's the code that should go in here? And it needs to be something that is going to result in the allocation of the amount of memory that we need. So to figure out what that is, what I want to do is see what NVCC does for local array allocation, because we need to generate some code here, but maybe we don't know what. So to do that, there's this example in the CUDA programming guide that shows you how you can allocate memory on a per thread basis inside a kernel. So it consists of a main function where you call this malloc test kernel, excuse me, and then inside the kernel, each thread, every single thread is going to be running this, so every single thread is going to be doing this malloc, and then it prints out the pointer that it gets, that this particular thread gets, and then it frees it as well. For the purpose of today, I'm just going to not worry about freeing memory. So I've got that sample here in the file ptda.cu. So it's just the code from the manual. And if I build that, then what we should see when we run it is, that so they launch 5 threads, and each thread gets a different pointer. So how did that work? So what I've got in the make file is I build that as an executable here, but then also build it to emit the PTX. So inside the PTX, if we have a look at ptda.ptx, then we should be able to see what it's done to allocate that memory. And the answer is that it contains an extern in PTX. This is a bit like prototyping the function in C. This is a declaration of the malloc function. And what it looks like is, so B64 is just 64 bits in PTX typing. So it's going to return 64 bits. It takes 64 bits, a 64-bit value. So the param 0 is the size so that you are allocating. And then when we look inside the function, there we are. Inside this malloc test kernel, we've got a call to malloc, and they're passing this param 0, which is whatever the size. So I won't trace back through the PTX, but it'll be the size that they were supposed to be allocating. Well, it came from RD, so I guess it was 123. So what we want to do in our code is also emit a call to malloc. There's a few things we need to do to be able to call that. So we're going to need the name of the function, malloc. And we're going to need the type of the malloc function. I can't remember the exact code that I need here, but I think there's something similar, a similar pattern slightly further down that I can borrow from. Oh, right. So we need to create a function type. Can I fit it all on the screen? So we want to, the type of malloc is a function type, and then the first argument to the function type constructor is the type that it returns. So to get a B64 out here, I'm just going to use 64-bit int type. That'll probably do for now. Next comes the list of arguments. So that is going to be, because malloc takes one parameter, that's 64 bits, I'll give it an IR.int type as well. That should be a tuple of arguments, so that make that a tuple. So got the name and the type. I think the next thing we want to do is we need to insert the prototype for this function, if you like, into the module that we're building. Essentially, we're sort of forward declaring it. So there's a helper function for doing that in CUDA or insert function, which takes a module. So I guess that's going to be builder.module. What I'll do, let's just start the debugger again so I can figure out exactly what it is that I need to do. Oh, but my code is possible. Try that again. So we've got CUDA insert function module. No module. So I had everything I needed. The module, then the type, and the name of the function. I have a funny feeling that I shouldn't be using builder.module. I should already have. Maybe oh no, I thought I already had the module handy, but I don't. And then finally, what we need to do is to call that function. So how do you call a function? Builder.call, the name of the function, the arguments that you pass it. Right, let's do that. Sorry, not the name of the function, but the function that CUDA gave us. So that should be, we need to pass it the size. Okay. That's all good. And that's just made me realize that we need to compute what the size is, because we have the shape passed in. So thinking it too wrong. So what should that size be that we passed to malloc? What we would like, I think what we would like to do is to start out with the size that an item in the array is going to be. So if the D type were in 32, then it'd be 4, for example. And then we're going to iterate across all the elements of the shape and build a multiplication that build a string of multiplications that's eventually going to give us the right size allocation. So okay, so we've got the D type. So it should be something like start off with a constant for the size because we know what the size of the D type is going to be. We got all the arguments that are type, and then value. So the type should be use a uint64, seeing as Mallet's expecting something 64 bits, and the value will be. Have I got D type handy in this shell? Item size? No. No. Bit width. I guess we'll go with the bit width divide that by 8. All of this implementation that I'm doing is starting to look increasingly hacky. I'm finding a path, some kind of compromise between what I know and what might work. And if I were going to actually submit this as a PR, there'd probably be a fair bit of tidying up to do first. Can I just ask if there's any questions or if anyone wants me to go back over anything at this point? Okay, then we'll carry on. So next we'll iterate over the shape and we will reduce, we'll multiply each size repeatedly by whatever we have at the minute. So let's see what this looks like if I print it out at the moment. Oh yeah, so actually maybe I don't need to do anything clever. Maybe I'll just need to do, we'll just need to multiply the current size by that size. Something feels wrong about this, but I can't put my finger on it. It might also be, I just want to go back to the LLVM documentation. Nope, sorry, LLVM Lite. And check what I should be doing for multiplication because, no, more, left-hand side, right-hand side, okay. Well, as far as I can tell from the documentation, I'm doing the right thing. So, so with that in mind, if we're in the local address space and it's dynamically sized, we'll start off with a size of one element, and then for each dimension of the shape, we'll multiply our current size by that. Then we'll add the malloc function into the module, and then call it with this size, and that should give us a pointer back to the data. That seems to make sense to me at the minute, but let's step through and see what happens when we actually go through that. So I'm just going to step till we get to that logic that we just added. So start off adding the size, and then it should probably multiply a couple of times. So it turns out that the shape type is not all int64. So what we'll just do is we'll add a cast. Should that be builder.cast? I'm going to have a quick look at the LLVM Lite documentation again. See if there's something about not bitcast, address space cast. Oh, sign extend, maybe. Oh, so we want to sign extend the value to that type. Let's try sign extension instead. What was the order of the arguments? It is the value first and the type. So this is the value. The type will be 64 bits. And if S is already 64 bits, that should just be a no op. So with that cast in place, let's try stepping through that again. Oh, spoiled everything. What's going on? Probably forgotten a bracket. Try that again. So stepping through to that. So starting off with the size, iterating first through. Okay, that's one multiplication. It seemed to work okay. And then we will add our malloc function to the module. So far, so good. And then we'll call it. Oh, okay, there's an exception. What's gone wrong? What's instruction is not iterable? Oh, right. Yes, because you need to give a call a list of arguments, not an argument. So that should be, it's one argument, but it should be inside a tuple. So let's just run through that again, start stepping through. I should move the breakpoint a little later in a minute, actually, because this is stepping through the same thing again and again. Hopefully this will, okay. So we've got through all that point to that point. Now what's going to happen? We're on this line. I do wonder what these three lines are about.
Which three lines?
Target data, LLD type, and item size. I think actually I probably don't need to worry about them because this has got nothing to do with the shape, nor is this, and nor is that. So let's just step over them. Would you be amenable to that plan?
So this is all to compute the item size, and your final size would be shape. I mean the product of all these dimension shape and times this item size.
This is just the size of one element, though, isn't it? It's got nothing to do with the length of the. I think this should all. There we are. Sorry, did that make sense? So,
okay, yeah. Yes.
Yeah. Okay. So next we've got to compute the strides. So I guess we've probably got a problem here again. Let's see. So computing the strides is a bit like computing the shape, except you do it backwards, and each stride is multiplied. You multiply what you had previously by the size of the current one size. Without getting too much into exactly what it means to compute the strides, let's try and only think about what we might need to change if one of these turns out not to be a constant. Now, the problem will be that this assumes we've got all constants in shape, I think. So it's probably going to fall over as soon as we go through that loop a time or two. Let's try it. So you can't multiply it into an extract value. Makes sense. So the idea here is that this builds a constant. Right, so k strides is going to be the variable that holds the tuple of strides, except it's no longer necessarily going to be a constant, and we can't just compute the strides by instead of doing this computation in Python, we need to generate the code that will do it in the generated code. Let's think about how much we might need to change here. Um, so instead of that should be reversed R strides. Feeling like instead of this no, wait a minute. But if we are dynamically sized, then do something. Otherwise, do the thing we did before, which was do the multiplication here. And also here, we are dynamically sized, then do something different. Otherwise, use the old computation. So what are we going to do if it is dynamically sized? Instead of doing the multiplication, we will, I guess we'll say, generate a multiplication instead, and that way our array of R strides should get populated with instruction or references to instructions that have computed the strides. And then what's happened with last size? It says last size, it's just the size. It's more like current size, isn't it? Shape. So that's just reversing it, so that shouldn't need changing. What that means is that here, these strides should just be a list of, not constants, but actually, I think here, if the current stride, what is last? We have got an actual int because one of the dimensions was an integer, then maybe what we should do is last stride. Which way around was it for get constant again? Was it the type then the value, or the other way around? Type then the value. So there we are. That way, we should be making sure that if we do have an integer stride somewhere, because it wasn't dynamic, then we'll get an LLVM value and not start trying to shove a Python integer in the middle of the LLVM IR that we're generating. And then, so that was reversing the strides. If this is canned in size, the K strides should be, instead of making it a constant, these will all be values. So K strides should probably just be equal to strides because we don't need to make everything into constants. If it was a constant, then it was made so in this branch. If it wasn't, then it was the multiplication here instead. Why is that giving me red? Oh. So I'll just try restart and step in. I think I should be able to get through to this line where this shape is turned into a constant without things blowing up, but let's see. Sorry, I'm a long way away from where I should be now, but hopefully if we iterate over the strides. Oh. Int object has no attribute type. Okay, let's think about that. Where were we here? First of all, I'm just going to take my breakpoint out from the top of the function and put the breakpoint just before this loop because I guess the problem is that last stride in the first case turned out to be an actual integer. So yes. If we do have a dynamic one, then oops. What we should be doing is making it a constant instead. There we are. That way we don't end up trying to build a multiplication of a Python integer and a LVM instruction. So hopefully we go in there. We go constant. Oh no, what have I done wrong? Made a total mess of this. Is it because should that be type?
Yeah, it should be.
Yeah, I'm mixing it. Yeah. So I mixed it up the front and back, and I've made the same mistake here as well. But I think thinking about it, I've been a bit freely switching between sort of the front end and the back end types a little bit throughout this. Not very idiomatic code that I'm writing here right now. Try that again. Okay, so now we have our last stride. Hopefully we can step through this loop where it builds the strides without, oh, okay, we're blown up for some other reason. Okay, so need to make sure that that is also 64 bits. I think all that have been, so it better be this one. Same thing as we had before. Need to sign extend up to 64 bits, I think. And have I got syntax error there because I've not enough brackets again? Probably. Oh no, or is it too many? No, the line's too long. Yeah, what am I doing? Hopefully I've just got that else at the right level of indentation. Because we're actually pretty much at time. So coding and panicking at the same time. But we seem to be able to step through that loop okay. So perhaps the panic has paid off. Let's reverse the strides. Hopefully our strides. This isn't dynamic shared memory. So we're about to get through to this line here where the shape is made a constant, which we're going to need to change next. I think we're nearly right at the end of this function. So we're at 1 hour. What do you want to do? I could spend a couple more minutes and try to make this appropriate for the dynamically sized case, or just wrap it up here, sort of inconclusively. What do you reckon?
Let's try to wrap it up. I mean to
make this work.
Make this work, yeah.
Okay, all right. I think all I need to do is similar to what I did above with the strides. I just need to do shape equals shape. Basically, don't make the shape a constant. if it's dynamically sized. Otherwise, it's not dynamically sized, it can be a constant. So that, from a quick skim, maybe we'll walk all the way through to the end of the function, because where did I get to before? I don't want to step through all that code again, given that we've only got a minute or minus 1 minute left. I'm just going to put my breakpoint here and see if we get there. Yes, okay. So, okay. Oh no. Oh, right, okay, just need a sign extension. But where does that sign extension need to go? Let's have a look at the exception again. Anyone know what they need to modify? Oh, wait a minute, I can go down the stack and see where I was doing wrong a little bit. So, also for some reason, my shapes are int 32s. So I guess what I was missing was, I'm not making them into constants. I do need to be sign extending them.
Isn't that a tuple?
Yes. S. So I should be doing a list comprehension. Did that make more sense apart from what I've done wrong here? Closing parenthesis doesn't match opening parenthesis. Okay, and I think I'm going to have the same problem here as well. So very quickly. What's wrong? Missed parenthesis again. Can we get that far? Oh no, I've got some error earlier on. So where's my breakpoint? List object has no attribute type. I guess we'll at least get here. Yep. Oh, it's because I should have put S there instead of strides. Trying to sign extend an entire list instead of an element of the list. Do this again. That's okay. That's okay. And we populate the array. Yes, and we're about to return array.get value. So now that we've managed to build all that, let's have a quick look at the module, see what sort of code it seems to contain. Hopefully we can see a call to, we can see a call to malloc. We're passing it .25, which is multiplying 23 and 24 together. And 24 was sign extension 21, which was one bit of that tuple, and what was the other thing we're multiplying? 23 and 24. 23 is another multiplication with 22, which was sign extension of 20. So basically we're multiplying the two elements of that tuple together with can't see where we've set the size of the item. Oh, 4. There it is, 4. So, okay, so we're multiplying 4 by the first element of the tuple and the second element of the tuple, and then we call malloc on it. So I have not been able, not reached the point of running this code, but at least look, the code generation looks kind of correct to me. And we probably better stop there, right?
Mm-hmm.
I'm curious as to whether this has been any help at all. It's turned out to be much more technical than I actually expected it to be. And I've had to rush through quite a lot of concepts, just coding without really explaining. So if anyone's got any feedback, I'd really appreciate whether that was a stream of consciousness of gibberish, or if it actually provided any insight.
Well, I like the way you did it. Like I was able to follow what you were doing.
Okay, thank you. I think this is pretty much a case of biting off probably about 3 or 4 times more than I could chew in one 1 hour session.
Yeah. But you did like really good progress.
Okay. I mean, if you come up with, if you watch it again or whatever, or you come up with questions, then feel free to ask them in the Numba Dev channel. If there's stuff that I could explain a bit better, then I'll try to do that in the chat, or whatever. Thank you for listening and persisting with me as I stumble through this task.
Thank you, Graham, for taking the time to do this. I think this will be very useful, just going through implementing something and then how a Numba developer will actually approach and think about all of this. I think this will be very interesting.
Okay.
For users. Yeah.
Thank you. Oh, no, shall I stop sharing my screen now?